Bismillahirrahmanirrahim. Right now we are going to start our presentation on multiple core computers. So, this is one of our topics in computer organization and architecture. And without further ado, I think we can just start our presentation. So, these are all our group members. There's 5 people, and then just like based on the suggestion of what slides should we talk about, I've pasted here. We'll follow the slides and stuff, and we'll talk about each and every topic in this one. So I will tell you what about the definition of the multiple core computers. So what exactly is this thing about? So if you take a look at history, uh, you know that we started with a single core computer, right? The first computer was actually a Turing computer. This one was back in World War II, but regardless, it all started with a single CPU, right? But nowadays, as technologies get more demanding and stuff, we need parallel programming and stuff. So we need to use multiple core computers. So whenever we have multiple core computers, we need applications to run in parallel to that course, so you can use all cores at the same time. Therefore, that is about multiple core computers. Back in the days, we had one course, and then it has evolved, and then now even we have 64 cores. So you can look at the picture right there. That one is about Threadripper Pro. It's very expensive, 28,000 ringgit. It has 64 cores, and there are probably more items out there with more cost, but it's going to get more expensive the more cost we have. The next one. Okay, so right now, Mm, about how multiple core processes work is in parallel execution. So each core has its own fetch pipeline, and our operating system, which is usually Windows or Linux, or only those two are the ones that are popular. They will schedule tasks onto the cores. For example, this one is a very simple example. You can look at the picture. A picture is rendered whenever the picture is split into 4 parts, so you can use all 4 cores at the same time. So this one, you can even look at the task division that I have placed down there. It is about the multiplication of 5 times 4 times 3 times 2. Whenever we are taking a look at single core processors, what they do is 5 times 4. And then what we get? 20. 20 times 3 is equal to 60. 60 times 2 is equals to 120. You see, now a single core needs to do the work 3 times. But let's take a look at a multi-core. In this case, it's a dual core. You see, 5 times 4 equals 20. At the same time, the second core is calculating 3 times 2, which equals to 6. Now, because they have both calculated things, they only need to use core 1 again to times 20 times 6, which equals to 120. This, of course, makes the usage of electricity down, because you actually also saving time at the same time by using both cores at once. So that is about task division. You see how developers use parallel programming, which is basically multi-processing. The OS is responsible to show how the core processor work between all cores, so they can adapt to multiple cores and depending on the specs of the computer. The next.
Good afternoon, everyone. Today we'll discuss how computers with multiple processors, also called cores, handle memory. Memory is like a computer's short-term workspace where it stores and uses information actively. On the left side, we see shared memory. Imagine a group of friends working on a big whiteboard. Everyone can see and write on it. In shared memory system, all processors are shown as blue boxes and access the same pool of memory represented by the yellow boxes. They share this memory through a memory access interconnection network that ensures they can all connect to it smoothly. On the right, we can see distributed memory. Here, each friend has their own whiteboard. They can directly write on someone else's. They need to send a message. Similarly, in a distributed memory system, each processor has its own dedicated memory. If one processor needs data from another, they communicate through a message passing interconnection network. Moving on to the next slide. Now let's compare these two systems. In shared memory, all processors access the same memory, like everyone using one whiteboard. They see the same memory space and work together seamlessly. This is common in servers is called uniform memory access, where all processors access memory at the same speed. In distributed memory, each processor has its own memory, like separate whiteboards. Processors cannot access others' memory directly, they must send messages. This is often used in supercomputers, where processors handle large tasks independently and communicate only when necessary. In simple terms, shared memory is like a shared workspace, while distributed memory is like individual workspace with coordination. Both approaches are powerful, serve different needs. Thank you.
Okay, let's now know about the advantage of multiple course computers. Here are a few the advantages. The first one is a higher speed. Multiple cores can run parallel threads, increasing overall computation rate. A four-core CPU can approach 4x the performance of a single core. The second one is energy efficient. Two lower speed cores can often match on a high speed core while using less power. This improves performance per watt. The third one is scalability. It is easier to add more cores in future chips than to keep pushing clock rates. And many workloads simple run faster as core are added. And the last one is cost and integration. Fewer chips stacked and more functionality per chip can reduce hardware cost.
Okay, so before moving on, what about the single-threaded application and multi-threaded application? I want to show you a few pictures first. So, looking at one of the video games, one of the most popular video games, Minecraft. This is a very old game. So fundamentally, it actually was very used on utilizing only one core. You can see the core usage up there, right? Only one core was used because this is a single threaded application. However, they have developed into multi-threaded application, but it relies heavily on a single core. Whereas in a multi-threaded application, even you can see that I've opened so much application on the right side. This is me using many multi-threaded application, WhatsApp, Google Chrome, and everything I've opened all at once. You can see that it actually distributed the work for the CPU to load and calculate things. So that is the introduction of single and multi-threaded application. As for the explanation, what application actually benefit from multi-cores? The most important one is probably gaming, because it's not just about calculating things. There's also graphics, which is what we'll get into the GPU stuff. But for now, we are just focusing on CPU. But modern games nowadays all use parallel processing, and thus it needs multiple cores. However, older games like Minecraft only uses single cores because it was made single threaded when it was developed. And also video editing and rendering, those things also need GPU, and of course it needs multiple cores. And lastly is scientific computing and simulation. Of course, just like the example that I've shown you, right, you can calculate a lot of numbers at once, thus saving a lot of time. That's it.
Now we will learn about the difference between multi-core systems and multiprocessor systems. So in the picture on the left side, we can see a single processor chip. It has multi-cores, core 0 and core 1. Both of them have their individual CPU and level 1 cache, but they share L2 cache and they are connected to system memory. On the right side, we can see two different processors. Each of them have two cores, and all of their cores have their individual CPU with their level 1 cache, and they have their each processor have their own shared L2 cache, and they're connected via a system bus, and both of the processors are connected to system memory. Let's move on to the next slide. Here in this chart, it shows the differences between multi-core versus multiprocessor in terms of definition, cores, and memory. So we can see that multi-core is multiple CPU cores in a single chip, and multiprocessor system is multiple independent CPU chips in one system. Cores. Multi-core processor usually has two or more cores per chip. It can be dual or quad core. And multi-processor system usually use one core per chip, but it can also be multiple cores per CPU. For memory, multi-core processor uses shared physical memory, and all cores see the same memory space, and multi-processor system can be shared or distributed. Next slide. Now let's learn about graphics processing unit, GPU. A GPU is a many-core processor optimized for data parallel application. It contains hundreds or thousands of simple ALUs or arithmetic units arranged into blocks, dozens of streaming multiprocessors. Each SM or streaming multiprocessor contains many CUDA cores, FP32 units, INT units, and special tensor cores for AI. Thank you.
Okay, now let's talk about the usage of GPU versus core processor. This slide compares the internal architecture of multi-cores CPU and GPU, showing how GPUs are used alongside CPUs to accelerate computation. As you can see here, a multi-core CPU, it contains few powerful cores which with arithmetic and logic units, control logic and L1 cache shares L2 plus cache across cores and also connected to DRAM, which is main memory, and the next one is optimized for serial processing and general purpose tasks. And here you can see GPU, it contains many simple alloys showing as a large area of green blocks. It designed for massive parallel processing and also it includes L2 cache and DRAM. It best suited for data plural workload like graphic, uh, rendering, and AI computation. Moving to next slide. Here is the usage of GPU versus co-processor. GPUs offload parallel workloads from the CPU, and a CPU handle general control, branching, and sequential tasks. GPU accelerates graphics, rendering, physics, image, and processing, and a system often uses both the CPU schedule task and handles input and output and gives computation to the GPU. Thank you.
Okay, so now we get into the GPUs. So recently you just heard me about GPUs and stuff. So what is the difference whenever we buy things, computers, when we go to a shop, they will talk about CPUs and the GPU. Even if you look at any laptop, you just open it, you can see the sticker right here. Just like mine is AMD Ryzen 7000 series and AMD Radeon graphics. So if you take a look at Intel usually the best Intel is i7 or i9, and the graphic would be Nvidia. So basically, yeah, you can see at the top right here, these are my specification for my computer. And the difference really about CPU and GPU is CPU calculates all the mathematical things, and GPU is has a lot thousands of cores for them to calculate the every single pixel and frames, because graphics takes a lot. We cannot simply just use CPU for this kind of work. It's quite a heavy work for us to for the computer to calculate graphics. So these are some of the popular companies in CPU and GPU. CPU, they have Intel i7, i9, and and also AMD and Apple also. GPU, usually you'll hear Nvidia and AMD also. So Nvidia and AMD is like shoving back and forth who is the best. It's basically like Coca-Cola and Pepsi. These are the two main companies that make GPU. Moving on, we can see the comparison of GPU and CPU. A CPU typically only has 16 cores with control logic. It's used for arithmetic problem, whereas GPU can have hundreds of even thousands of cores. You can even look at the slide before. You see, the difference is only like 4 cores here, and it has multiple CPU, whereas the GPU has thousands of cores. And as for parallelism, um, a GPU is optimized for low latency workload, so it doesn't require fast response. However, for GPU, it is optimized for high parallel workload, which is mainly graphics. So the primary use for GPU is it acts as the brain of the computer and runs Windows. Yeah, CPU. CPU is the brain of the computer, whereas GPU is mainly used for rendering pixels and graphics.